Hi everyone, it's Paul, W2PAK. nfed half-wave antennas have been around for a while. The reason is they're easy to deploy, they're cheap, they're easy to build, they're effective, and they can be multi-band. Today, we're going to look at the theory, we're going to simulate one, we're going to build one, including the 49-to-1 Unun. We're going to test it, and finally, we're going to have a few QSOs. Come join me. In order to understand how an nfed half-wave antenna works, we first need to understand how a dipole works. This is a complete antenna system, so you can see you have the transceiver, you have the transmission line, usually a coax, and then this is a balance system where half goes one way, half goes the other way. Here you have a quarter wave and a quarter wave. Now, if you look at the voltage at the end of the antenna is the highest, and in the middle is the lowest. So the voltage is going to look something like this. Whereas the current is going to look kind of the opposite, where at the edges of the antenna, the current is 0. In the middle, the current is the highest. The reason the current is 0 at the end is simple. There's nowhere for the current to go. And so the current is going to look something like that. Now, what happens here is, so if this is V, and this is I, okay, if you look at the impedance, so Z, we'll call it Z0, equals to V over I. So here you have very low current, so V over I here is going to be a high number over a low number, so Z is going to be very high. In the middle, you have V very low, I very high. Sorry, it's not very symmetrical. So Z here is going to be relatively low. It's going to be around 70 ohms, on the order of 50 ohms or so. So this is how this works. Now, if you move the feed here from the middle to, you slide it one way or the other, you're going to get the same kind of response from the antenna. It's still going to be a complete antenna system, but the impedance is going to change depending on where you move it. So if we're going to do an nfed here, the Z is going to be very high. And so we're going to see that in a second. Now the cool thing about this antenna, one of the nice things about a nfed half-wave, is that it's a multi-band antenna. So let's say the first frequency we're targeting is 3.55 megahertz. Okay? The nice thing about this antenna, it's going to be resonant. We'll cut it to make it resonant at this frequency, but at double this, it's going to be resonant. So if you multiply it by 2, that's going to be 7.1 megahertz. It's also going to be resonant at 3 times that, which is 10.65 megahertz. Does that look familiar? Then 4 times will be 14.2 megahertz. So look at all these bands we're getting. And then 5 is going to be 17.75 megahertz. 6 is going to be 21.3 megahertz. 7 is going to be, you probably already guessed, 24.85 megahertz. And 8 is going to be our last 10-meter frequency here. So it's going to be 21. Hold on, I have a calculator on the side here. Give me a moment. 28.4 megahertz. So look at this. This is cool. 80 meters, 40 meters, 30 meters. somewhere, okay, so this is 20 meters. This we'll call, this is meters. This we'll fudge it. We'll say it's 17. It's close. 21 meters, and I'm sorry, 21 meters. What am I saying? 15 meters, 12 meters, and 10 meters. Look at that. With one nfed, if you do a 40, if you do an 80, you get all these frequencies. Now, what we're going to do for this is we're actually going to start with, we're going to cut it to somewhere around here. So we're going to get the 7.1. We're good. So that's going to be 1 times. We're going to get the 14.2. We're going to get the 21, and we're going to get a 28. So I'm going to make, in this video, a 4-band, but you can make this whole thing. You can even go down to 160 if you have the room and do the same kind of thing. All right, now I want to simulate this. I want to show you, we talked about the impedance and these harmonics. I want to show you in simulation how this works. So this is COCO NEC. We're simulating a dipole antenna that's resonant in the 40-meter range. So it is somewhere around 66 feet or 33 feet on each side. It's called, of course, it's fed in the middle in this case. We're going to look at the Smith chart, and in the middle we see that the impedance is 72 ohms or so, which is what we predicted. And if we look at the SWR in this case, we can see that it is resonant at around 7.2 is the minimum SWR, and it's pretty much as we would expect. Now we're turning to the nfed antenna. Of course, it's fed at the end. It also is designed to work in the 40-meter band, so it's also somewhere around 66 feet. Looking at the SWR, so using the fundamental kind of harmonic for which it's designed, it's as expected. Don't forget that this system is very high impedance, so the SWRs here are meaningless. So in the azimuth, it looks like that. In the elevation, it looks like that. You can see the takeoff angle is rather high here. And of course, the impedance is really, really high in the order of kiloohms. And that's what we expected. Now looking at the 20-meter band, you can see that there's also kind of a dip and, same type of impedance, very, very high. Notice that the radiation pattern changes in the 20-meter band. Notice that the takeoff angle is better here. This is the 15-meter band, and if we look again at the Smith chart, of course, the same situation, very high impedance, but again, we have a different radiation pattern. So this is the azimuth, and if you look at the elevation, you'll see that also much different. 2 lobes here, but the takeoff of the angle of the lower one is even lower. This is the 28 megahertz or 10-meter band. Again, the patterns are different here. This is the azimuth, and this is the elevation. So overall, the patterns change. The other characteristics do not change very much. All right, let's talk about the 49-to-1 Unun. So this is the circuit. So the whole idea of this circuit is to balance a 50 ohm coax input to a very high, on the order of kiloohms antenna. So that is what we're trying to achieve. Now, transformer theory. Let's talk about this a little bit. So if we have, say, this is N1, and this is the number of turns 2, N1 and N2. If we're trying to calculate how many turns we need, if we take Z2 over Z1, if this is Z1 and this is Z2, then that is going to equal to the square of N2 over N1. So in our case, we want a, let's say 2500. That's going to make my life easy calculation-wise. So if Z2 over Z1 is 2500 over 50, that is 50. So that's the ratio. So we want 50 to equal to N2 over N1 squared. Well, if we take a 7-to-1 ratio, then we would get 7 squared is 49, close enough. And so in this case, we're going to do 2 turns and 14 turns, and that will give us the matching that we're looking for. Now, this little capacitor helps with broadening the bandwidth of the Unun. Without it, it's going to go up to probably around maybe 18 megahertz or so, where you have a decent SWR. With it, it goes all the way up to the 10 meter band, which is what we're looking for. So that's the theory. Now let's talk about materials. So we have a toroid, and it's going to be ferrite. And the question is, what kind of toroid do we need? So the ferrite that we need is going to be based on the material and the size. So the mix is the material. The mix is going to be dictated by the maximum frequency we want to use it for. And the size is going to be dictated by the power that we want. So let's say we want to build 3 different systems. I know there are people looking for different powers, and the question is, what kind of material do I need for this ferrite? And if you're looking for QRP, my advice is to use the FT, say 140, 43, and all you really need is 1 toroid to do that. If you're looking, say, from 100 watts to like 350 watts, and that would be PEP, then you're looking for maybe FT240, 43. And if you use 2 of these toroids, so basically you take 1 toroid and then you take a second toroid and you glue them together, then you're going to get, up to 350 watts. If you want, say, around 1200 watts PEP, then you should use the FT240 and use the 52 material and use 2 of those. So this is kind of a good basic guideline of, depending on how much power you need, which material and how many toroids you need. So QRP, you can get away with a 43 and a smaller toroid, and you can only use 1. If you want kind of medium power, we'll call it, this is low medium power, then you're going to use the FT240, and you're going to use a 43 material. You can use 2 of them. This is what we're doing, by the way. And then if you want high power, you do the same thing. You just use an FT240 with a 52 material, which are much more expensive, and use 2 of them. Now let's build this thing. So this is the toroid. This is the 49-to-1 Unun. We're going to be winding 2 turns of the primary and then 14 turns of the secondary. The primary and the secondary are going to be twisted together for the first 2 turns. And this is the little schematic. I found this from KM1NDY. I like the way he made the schematic, A, and B, I like the way he did the winding, and so I'm going to be following him. So these are the 2 toroids. I'm going to super glue them together, do the winding, and then probably with a couple zip ties, I'm going to connect these together. All right, so it's all wound. I used 1.2 millimeter enameled wire, and here on the, for now I just kind of took a flame and took off the enamel so we can test it. The tricky part is, so these first 2 turns need to be wound together, the primary and the secondary, and then the rest of them are just going to be the secondary. So anytime it goes through the hole, it's a turn. So 1, 2, 3, 4, 5, 6, 7. Then notice the 7th one comes out, and the 8th one picks it up from the other side, and then 9, 10 through 14, and the 14th goes underneath. So that's the way it works. We're going to test this in a second to see what the SWR is. I needed about, I would say, if you have 8 foot of enameled wire, you should have more than enough. So we're going to be testing this. I'll be right back. All right, so I'm done here. Basically, you can see the toroid is here. I tacked it down with a little bit of RTV. This is the antenna side. I've made a little ground. Capacitor is right there. And so we're testing it. So there is a 4.7 kilo ohm resistor here. You can put anywhere really between 3 and 5. I don't think this is showing up very well there. That's better, I think. There's a little glare from the light above. You can see it's pretty good. So at 3.7, it's SWR 1.3, and it's pretty flat. It goes up a little bit to 1.6 on 10 meters here. So really between 80 and 10 meters, it's nice and flat, and it looks like it's doing the job. So I'm excited. Let's take this out. Let's string an nfed and see what this puppy can do. It probably could handle around 350 watts with these two, with the 2 cores. So yeah, let's go out and check this out. All right, so we deployed the antenna. It comes out of a window. This is the 49-to-1 Unun. The antenna wire is on the top, of course. The bottom is the connector to the transceiver. I do not have a ground counterpoise here. I use the coax shield, basically, or the coax for the counterpoise. Looking at the SWR, this is the entire band. You can see that there are 4 distinct bands, as we would expect: the 40, the 20, the 15, and the 10 meter band. Looking at the 40 meter band, you can see that there's a very nice SWR. The lowest here is about 1.1, even less than 1.1, as high as 1.6, which is really good. And then the 20 meter band goes down to really 1.0 here. And the 15 meter band, also very good, 1.2, 1.3 SWR. And finally the 10 meter band, also very good, around 1.3, 1.4 or less. So SWR wise, this is really very nice. Let's start with seeing what the receive looks like, and then we'll do a transmit, and we'll see how this performs. So let's see how this performs in real life. This is the 40 meter band. All right, so this is a good signal, S9 plus a little bit. And this is my vertical antenna, which is actually very good. It's on our dock over salt water. It's pretty optimized. And I'm going to go to the nfed. So the noise floor went up, and this is S9 plus 5, we'll call it, at the peaks. Back to the vertical. So maybe a 5 dB difference, something like that. All right, so that's 40 meters. Let's go to 20 meters. Okay, S9 with this gentleman. Back to the nfed. Noise went up. Same. So the signal strength here is about the same, but the noise floor went up. Call it S2, S3, vertical, nfed, noise went up. 2S3. So it's definitely noisier. Let's go to 10 meters. Alright, so this is 10 meter band. This is with the vertical. Let's look at the noise quickly. Noise comes up a few dB. Okay, so S9 plus, say, 5. And about the same with the nfed, but that noise comes up quite a bit. Okay, so for the transmit side, I used Whisper, the weak signal propagation system. You can see that many stations in the US heard my signal. I used about 20 watts, by the way, with the nfed. You can see many signals in Europe heard my signal. It looks like one in Chile, they heard me. This is the 20-meter side. Even better, also US and Canada, many in Europe, and one in Australia. Very nice. Looking at the 15 meters, same situation. Many heard me. Also South America. I believe that's Brazil. Again, the map is a little small. And then this is on the 10 meter. Many in Europe. One in, I think that's Iceland. One in right off the coast of, it's one of the islands in Africa. Overall, this did a pretty good job, I would say. So I think the next thing we're going to look at, let's do a few QSOs and see what kind of reports we get. Let's make some QSOs. Let's start with a 10-meter band.
Whiskey 2 Papa Alpha Kilo. Hi Paul, thank you for the call. You're 5 and 7 in Northern Ireland, QSO.
Whiskey 2 Papa Alpha Kilo, got you in there, Paul. You are 5757 in the boat park, QSO.
We looked at the nfed halfway antenna any which way. We talked about theory, we simulated it, we tested it, we had a few QSOs. I would say this antenna is a great beginner antenna. It's great for quick deployment. It's very easy to make. It's cheap. You can deploy it anywhere. I hope you had fun watching the video. I had a lot of fun making the antenna, making the video. If you want more content, please subscribe. 73, my friends.